Welcome back, Highlanders, as we continue our journey in our climb up the environmental economics mountain. You've conquered another base camp by going over that microeconomic theory. Now we're going to get into some environmental policy stuff, starting with Chapter 5, finding the optimal level of pollution. When we conclude with that chapter, then we're going to get into examining potential solutions and market trading strategies. Both these chapters do involve a lot of graphs and math, so be ready for that. And then chapter 7 and 8, we kind of start to ease up, particularly on the math, but even on the graphs a little bit as well. So with that in mind, let's go ahead and get started by talking about how to find the optimal level of pollution. Right, so again, remember that there is a certain amount of imperfection that might be economically efficient in the world, right? And so reducing the level of pollution down to zero might not necessarily be optimal. So what would be the optimal level of pollution? And that's what we'll be getting to with this particular chapter. So here's our quick overview. So the first thing we're going to talk about is minimizing total pollution costs as measured by both damage costs and abatement costs. When we talk about damage costs, we're going to be talking about emission damage, ambient damage, and marginal damage cost graphs. And then when we get into abatement costs, and we'll take a look at the marginal abatement cost graphs. We're also going to talk about the optimal level of pollution and how to calculate that. That's where our marginal damage cost is going to be equal to our marginal abatement cost. And then probably starting with the next video, we're going to combine the optimal level of pollution with this idea of the equal marginal principle. And then we are going to get into how enforcement costs influence this optimal level of pollution and how changes in technology are going to influence this optimal level of pollution. All right, so without further ado, let's go ahead and get into it. So when we're talking about total damage costs, there's a couple different kinds of damage costs that we're going to refer to, the first of which being called emission damage. And so emission damage function is basically the connection between the quantity of a residual emitted from a source or group of sources and the resulting damage from those emissions. Right, so when you see smokestacks releasing pollution out into the sky, right, what is the damage caused by that pollution that those smokestacks are emitting? Right, we can actually calculate this. In fact, the World Bank has done so. Right, so World Bank data has shown us the amount of estimated particulate emission damage caused by pollutants as measured by U.S. dollars. And you can look at this for most countries have data. Just go to their website. So for example, if you wanted to see the United States, you just click on this link there. If you want to see how, say, the United States and China compare, then again, you just click on this link here. Right. With that in mind, I'm going to go ahead and escape the full screen mode and show you what those websites look like, which is what I would do if we were sitting in a face-to-face class. All right, so again, if you were to click on that first link, then you would get the particulate emission damage from caused by the United States, again, as measured in current U.S. dollars. And as you can see, back in 1990, we were at about $8.81 billion, right? Whereas over here in 2017, I think is the latest year for which they have data, right? It's at $23.052 billion. Right, so as you can see, it's pretty significant, the amount of damage being caused by these emissions. If you wanted to, say, add China to that graph, again, you can just click on that second link, and you can see that as much as the United States has been increasing its emission damage, China even more so, given that it's a bigger country with a much higher population. If you look at their 2017 number, there it is. 34.018 billion is what you're looking at there, compared to looks like just 3.68 billion back in 1990, right? So in a span of about 27 years or so, again, they've increased the amount of pollution damage that they're causing by over 10 times or tenfold. With that in mind, if you wanted to look at any other country, you can certainly do so, right? Just click on the country that interests you, right? So like another real populated country that you might want to check out might be like India. So if you want to check out India, just go to India here. They're in alphabetical order. Click on that, and you can add India to that graph, right? And as you add India to that graph, you can see that they started out higher than China, but just slightly lower than the United States. Well, I've ended up lower than both right here at 20.284 billion being the amount of damage that their emissions are causing there in 2017. Right. So again, if you're interested, you can check out any other countries that interest you. Those links are there for you so you can explore that on your own just by opening up these PowerPoint slides and clicking on those links and checking out these different countries. Right, so keep that in mind as you might have to use these links in a future homework assignment. Right, so with that in mind, let's go ahead and get back to it. So that's always a fun part of the class, right? Getting to explore all this data and showing you where it is. Right, now another type of damage out there is the ambient damage, right? And an ambient damage function is the relationship between the concentration of particular pollutants in the surrounding environment and the resulting damages. Right, so with that in mind, I feel kind of a need to explain the difference between emission damage and ambient damage. So emission damage is essentially the damage caused by the emissions that are being released right now. Right, so those numbers you saw for like the emission damage in 2017, that was the amount of damage that was being caused by what was being emitted in 2017. Ambient damage is a little bit different in that it's essentially the damage that is the result of kind of the concentration of pollution in the environment as the environment currently stands. So in other words, as we emit stuff into the environment, then we are kind of adjusting or changing our environment. And so the amount of pollutants in our environment could be resulting in some damage being caused to us in terms of our health or lower ability to produce. And that's what we call ambient damage. So like emission damage might be the tons of something being released into an atmosphere. So like the tons of carbon dioxide that are being released, what is the damage being caused by that? Whereas ambient damage might refer to like the parts per million of something in an atmosphere. Or in other words, kind of what does our environment look like as a result of all these past pollutants, right? So for example, the air around us, as any scuba diver will be able to tell you, is about 79% nitrogen and 20.9% oxygen, with about 0.1% made up of other stuff. That's what the air is usually concentrated as. However, if we release a whole bunch of pollutants into the atmosphere, it might change that concentration. The kind of damage that's being caused as a result of that change in concentration, that is what we refer to as that ambient damage. Right, so the World Health Organization estimates that fine particulate matter causes 25% of lung cancer deaths, 8% of chronic obstructive pulmonary disease deaths, and 15% of ischemic heart disease and stroke. This is from a study in 2017. Once again, you can click on that particular link to take a look at some numbers from the World Health Organization. Once again, I've kind of already pulled those up for you. So it depends on what you want to look at here, but one thing that I don't want to say is fun to look at, but might be interesting to look at is mortality from ambient air pollution, right? So you can go ahead and take a look at a world map to see how these countries are being affected by their ambient pollution. And so this DALY statistic, this is disability altered life years is essentially what we're measuring there. So how many years of life have been affected as a result of this ambient air pollution per 100,000 people as measured in 2016. So if you look at the United States, right, you see a number of like 516, right, in 2016, right? Whereas if you look at something like China, again, you're going to see a much higher amount, about 1,830. And again, you can kind of look at these countries and take a look at the different statistics there to see, again, how they are being affected by the ambient air pollution in the world. Right, so that's just one of several statistics you can look at here from the World Health Organization. Of course, if you pull up their website now, they're going to be most focused on coronavirus stuff as a result of our recent history, right? But again, if you want to look at their air pollution statistics, you can certainly find that there as well. All right, so again, there's a few places to get statistics if you're interested in doing any further research in those areas, right? But again, these are the kinds of damage functions we're going to be looking at when we look at things like total damage costs and marginal damage costs. So with that in mind, our marginal damage function shows the change in damages stemming from a unit change in emissions or ambient concentration. So our marginal damage cost is what is the change in total damages resulting from the change in emissions, or again, the change in ambient concentration, if that's what you're studying, right? So for example, how much does, say, an increase of 1 ton of carbon dioxide in the atmosphere, how much damage does that cause? That is the marginal damage cost of that emission. Or what is the damage caused by an increase in one, say, part per million change in the atmosphere? Again, that would be the marginal damage cost of that particular change. All right, so keep that in mind. Now, remember what I told you back in Chapter 3 when we were looking at marginal cost curves and the different kind of shapes that they might hold? Remember that every curve tells a story, and you need to be able to look at a graph and tell me or whoever you're doing the research or study for what story it is telling. So with that in mind, let's go through a couple of examples. Right. So first example, let's say that there's a pollutant out there, and this is true for most pollutants, where the marginal damages are small when emissions are low, but as emissions grow, damage gets more severe. What would a graph of that particular pollutant look like? All right, so let's go ahead and graph this out. So again, we're going to draw a graph here, and on the vertical axis, we're going to be measuring damages. And like the World Bank, we're probably going to be measuring damages in terms of, say, maybe US dollars. And then on the horizontal axis, we're going to be measuring emissions. Again, we might be measuring it in, say, tons per year. Maybe tons of carbon dioxide emitted every year. Right, so again, you might not have any damages from the first few tons of carbon dioxide as a result of the Earth's assimilative capacity. Remember what that definition means? It means the Earth can handle a certain amount of pollution before it suffers any negative effects as a result. Right, so let's say that anywhere between, say, 0 and we'll call it E1 level of emissions, right, the Earth's not really going to suffer anything from it. But then once you start to emit beyond that level, then you're going to start to see some costs as a result. And so you might have a marginal damage cost curve that looks something like that, right? So again, there's no damages at first as long as the amount of pollution is below the Earth's assimilative capacity, right? But then after an increase in the number of emissions beyond that assimilative capacity, you're going to start to see some damage. Now that damage is going to be low when emissions are low, but that damage is going to grow as those emissions grow with it, right? So again, the more emissions we have, then the more damage you're going to have as a result. So keep that in mind when you're looking at a curve like this, what that means. Now, can you change the Earth's assimilative capacity? Well, to a certain degree, you can, right? Remember, we talked about with the Green New Deal some ways that you can do that. For example, if you plant more trees, those trees take that carbon dioxide and convert it into oxygen. So the more trees we have freestanding, then the higher the Earth's assimilative capacity. So there are things that you can do to adjust that, but again, it just depends on the Earth's current state. Now, you could also have a situation where the substance is highly toxic, so that it has a deadly effect at even low levels of emissions. So what would that look like on a similar graph? You want to graph that out? So again, we're measuring damages up here. Again, maybe in terms of US dollars. And then once again, we're going to be doing emissions down here. And again, those emissions might be tons per year, right? And by the way, when we measure those emissions, we usually abbreviate them with an E there. All right, so with that in mind, what might it look like if this toxic substance has a deadly effect even at low levels of emissions? Well, you might have a graph that looks, or a curve that looks something like this, right? So again, your marginal damage cost curve, right, might look like that, whereas even with a very low amount of emissions because of the toxicity of this substance, it's going to create some problems for the environment. Again, those problems will increase the more the substance is being released into the environment, but again, even at its initial level, it could be quite toxic. So this might be like a Chernobyl-like accident here. So again, radioactive waste might have this characteristic or this graph associated with it. All right, so that's what our marginal damage cost curves might look like if we're looking at emission damage functions. Let's go ahead and take a look at a couple more damage cost curves. When we're taking a look at these ambient damage functions, right? So again, you could have a situation where damages rise rapidly with low levels of concentration, and then start to level off until we reach a higher concentration, and that's when damages are going to start to increase rapidly again. So what might that look like on the graph? Let's go ahead and take a look. So again, as we're graphing this out, we're going to be looking at damages on the vertical axis. Once again, maybe measured in dollars. And then we're going to be taking a look at ambient concentration this time. On the horizontal axis. Because now we're looking at those ambient damage functions rather than those emission damage functions. And again, that might be usually measured here in parts per million. So ppm. All right. So again, if you have a situation where initially it's going to cause some damage, and that damage is going to rapidly rise even with low levels of concentration, and then it's going to level off but then start increasing rapidly again, then you might see a curve that looks like this, where it has a steep slope in the beginning, and then again kind of levels off, and then again you see it to start to increase again. Right, so what might be an example of something that could give you a marginal damage cost curve like this? Right, well, there are some pollutants out there like carbon dioxide that again could affect the air quality, right, based on the parts per million in the atmosphere. And that could affect certain groups of people a little bit more in the beginning. So for example, if somebody is asthmatic, they might have a more difficult time with this level of pollution in our environment. Right, so in other words, a increase in our parts per million could really hit asthmatic people pretty significantly. Right, so again, these are the people being affected all the way up towards maybe this level of parts per million. So we'll call this ppm1. And then everywhere between ppm1 and ppm2, these further increases. I mean, they've already hit the asthmatic people pretty hard. Right, everybody else probably won't notice that big of a health change or health risk, right, with those increases between ppm1 and ppm2. But then as you further increase the concentration of carbon dioxide in the atmosphere, whether you're asthmatic or not, it's going to start to hit you hard. So again, even the less vulnerable people or less vulnerable populations are going to be affected by this. So again, as you continue to increase the amount of ambient concentration in the atmosphere, then you're going to see those damages start to rise significantly again. Again, once you get past a certain point, it's going to hit everybody hard, not just the most vulnerable populations. Right? So the idea behind this graph is that anywhere between 0 and ppm1, it's the most vulnerable populations that are hit first. And then after ppm2, whether you're vulnerable or not, you're still going to get hit pretty hard by these increasing amount of damages, or increasing amount of ambient concentrations. So with that in mind, what if there's a situation where there's no damages at first, but then damages rise steadily and rapidly as the concentration increases? So again, we're measuring damages over here in terms of dollars, and here we might be measuring ambient concentration. That's parts per million over here, right? Now again, once we're at a certain level of parts per million, you might not necessarily see any damage at all, right? But then once you get past a certain level of parts per million, you might see again damage steadily rise as a result of a further increase in ambient concentration, right? So if that's the case, then again, you could see a curve that looks like this. So you could have a marginal damage cost function that looks something like that, right? So again, there could be some pollutants out there that there's a certain amount, again, that the Earth could handle before we are going to suffer any severe negative effects. So we talked about human waste being emitted into our water supply, Remember, there's a assimilative capacity of our water supply to handle that level of human waste before it really causes any considerable pollution. But once we get beyond that assimilative capacity, then right, it's really going to start to cause some problems for the people who are using that water supply. So that might be an example of the second graph, right? Is that the parts per million of human waste in the water below a certain level doesn't really cause any negative effects. Once it gets above a certain level, as long as that level keeps increasing, the damage caused by those increasing parts per million will also start to increase. So again, make sure you know what story a curve is telling, either on a quiz, exam, or just in life if you're working for somebody at any kind of firm that does these kinds of studies, right? Again, know what story that these graphs and curves are telling individuals so that you can interpret them correctly for whoever it is you work with or for. Okay, so again, every curve tells a story. Know that story. So let's go ahead and move on. All right, so using our marginal damage cost curves, let's talk about how to find total damage costs. It's pretty easy to do. Total damage costs can be measured as the area under the marginal damage cost curve at any particular level of emissions, right? So in other words, when you have your marginal damage cost curve, right, at whatever level of emissions, the area under that particular marginal damage cost curve is going to represent our total damage costs, right? So again, make sure you can interpret that on a graph, and we'll go through an example here in a minute. Right, just know that if our marginal damage cost curve shifts up, then it means that more damage is being caused by the next emission. So again, know what that graph is telling you and be able to mathematically interpret what's going to happen to total damage costs when your marginal damage cost curve shifts. So let's go through an example of what this might look like. So again, I'm going to exit the full screen. I'm going to start to get into some different colors here, but let's go ahead and draw out a graph. So we got a vertical and a horizontal axis, right? Again, you've got damages that we're going to measure in US dollars over here, and then we've got emissions that we're going to measure on the horizontal axis. And again, we're just going to abbreviate that with the letter E. It's an ugly E, but there you go. All right, so with that in mind, again, you could have a situation where between 0 and we'll call it E1 right here, you're not going to suffer any negative effects from these emissions. Again, that would be the Earth's assimilative capacity, or how much pollutant that the Earth can handle before suffering any of these negative effects. And then you could have a marginal damage cost curve, as we just talked about, looking something like this, rising up from E1. All right, so let's say that we decide to pollute all the way up till E2, right? So wherever E2 hits that marginal damage cost curve, that's going to give us the marginal damage cost at that level of emissions, right? So for example, if that marginal damage cost is $10, right, then that means that the cost of one more emission to us as a society would be $10 when we are at E2. Right, so again, just kind of interpret what's going on in this graph. If we are at the curve MDC1 and we are at E2 as our level of emissions, right, then the total damage cost is going to be represented by the area under that MDC curve when we're at E2. Or in other words, it's going to look like this area here, which yes, we will be able to calculate by the time this chapter is done. Right, so again, this is going to be our total damage cost when we are at E2. So again, our total damage cost is represented by area A. Right, this being what we'll call area A here. Right, so with that in mind, again, just remember that the cost of one more emission is $10. That's the other thing that this graph is telling us. Ooh. Clean that up a little. So the cost of one more emission Again, when we are at E2 is $10. Now, what happens if this marginal damage cost curve were to shift for some reason? And we'll talk about some things that could cause this marginal damage cost curve to shift here in a minute. But let's say it were to shift up. So let's say our marginal damage cost curve started to look something like this. Right. Well, what happens when we're at this MDC2 curve at E2? Right. Well, now we're going to go all the way up to the MDC2 curve at E2 to figure out two things. First, what is our cost of one more emission in terms of the damage cost caused by that emission when we're at E2? Let's say that I give that to you here as 20. Right. So again, the cost of one more emission when we're at E2 when we're operating on the MDC2 curve is $20. And not only that, but it's also going to affect the total damage cost, right? That's also going to include this area here, in addition to our original area. Remember that total damage cost is the area under the marginal damage cost curve in question at a particular level of emissions, which in this case we're saying is E2, right? So total damage cost is equal to area A plus B now, right? So if this is area B, right, if you add A and B together, that's going to be our total damage cost when we're at E2 if we're on the MDC2 curve, right? And the cost of one more emission, again, it's going to be important that you know how to interpret these curves when we start doing the math here. As you can imagine, I'm not always going to tell you. I'm going to make you find it at some point. But the cost of one more emission here is $20, right? So again, if that MDC curve shifts up, then you're going to have more total damage costs at a particular level of emissions, and the marginal damage cost of one more emission when we're at that level is going to be higher. So what might be something that's going to shift up this marginal damage cost curve, right? What might be something that, again, might cause that curve to be higher so that the same amount of emissions cause more damage? Let's go and take a look at some things. Right, so here are some potential shifters of our marginal damage cost curve. One is the differences in populations exposed. Right, so for example, there are some places that just have a higher population density, right, than other places, right? So if you're living in, say, New York City, the same amount of emissions is going to affect more people than if you lived in, say, some area of rural Montana, right? So again, there are certain populations that are just going to be hit harder because there's more people in those populations, and that could be something that shifts up our marginal damage cost curve, right? So again, differences in population exposed could be one of those things. Right. The more people there are to experience the negative effects of this pollution, right, then the more damage it's going to cause people in terms of health or those disability adjusted life years. It could also be the not only differences in the number of people, but maybe the percentage of that population who again suffers from some pre-existing conditions like asthma. Again, they could be disproportionately affected by certain levels of pollution in such a way that it would shift up that marginal damage cost curve. Right, so if you have the same 1,000 people in two cities, but one city has a lot more people who are asthmatic, right, then again, that MDC curve could be higher for them. At the same number of emissions, could cause more problems for that more asthmatic population. Another thing is different time periods. So the same level of emissions at two different times could yield substantially different levels of damage depending on, again, the natural environment. For example, there are certain temperature inversions that could trap the pollutant over a city and produce a relatively high level of ambient concentration compared to when the pollution is allowed to be blown downwind and out of the area. For example, if like winds are low and pointed in the right direction, then the pollution in Los Angeles, right, won't affect Riverside nearly as much than if those winds are blowing all that pollution from LA into Riverside. So for those of you who have lived some time in Riverside, you know that some days are smoggier than others, and that really depends on when where those winds are blowing and where they're taking all that pollution that's being emitted in Los Angeles, right? So sometimes the same level of emissions in Los Angeles could affect the people in Riverside more drastically, and then at sometimes those same levels of emissions could affect the people in Riverside less drastically. Right? Again, it depends on what's going on with the wind and other conditions in the environment. Right. So again, sometimes it just depends on what's happening there in terms of those emissions settling over a city or being blown away or being moved to other cities. And then something else that could affect where we place this MDC curve are new scientific estimates on the impact of this pollution. So if we find out that this pollution is more harmful than we originally thought, that could be something that shifts that marginal damage cost curve up and again yields more total damage costs and a higher cost per emission at the same number of emissions. Right. Now, it could also be the case that we find out this pollution is maybe less impactful than we originally thought, in which case it might cause that MDC curve to shift down. So again, new scientific estimates or new ways of looking at the problem could yield some different results that would cause that MDC curve to shift. Right. So with that in mind, kind of understand what that MDC curve tells us, and again, things that could shift it. All right, so how much pollution is the right amount? It is, of course, tempting to say that society should strive for emission levels where the marginal damages are zero, right? In other words, as we talked about in our earlier chapters, the Earth does have some assimilative capacity, so maybe we don't need to keep pollution at zero. Maybe we just keep it at the point where the damage is zero. That would be nice. That'd be maybe a nice world to strive for. But even then, we might not necessarily want to strive for a situation where marginal damages are zero. In other words, not only should we maybe allow some pollution because there's some that the Earth can handle, but we might actually be in a situation where we should allow some pollution above that assimilative capacity, or at a point where it is creating some marginal damages. Right? In other words, not only should we not have the number of emissions be zero, but we might not even be in a situation where the damages being caused by emissions should be zero. Right. In other words, there might be an optimal amount of pollution that is non-zero, right? And there might be an optimal amount of damage costs that are non-zero as well. And the reason why that is the case is because these things called abatement costs. In other words, it is costly to get rid of pollution. So in addition to the damage that pollution causes to the environment, there's also cost to getting rid of that pollution in terms of maybe reduced production or the actual cost of cleaning up any pollution that's already happened, right? And based on those abatement costs, it might not be in our best interest to, again, get damage costs all the way down to zero. So abatement costs are the cost of reducing the quantity of residuals being emitted into the environment, if we're talking about lowering those emission damages, or again, the cost of reducing the ambient concentrations of pollution, if we're talking about reducing those ambient damages, right? So for example, if we have a factory that decides to clean up its production process in such a way to reduce the amount of waste and emissions it has, right, could be a cost to that, right? There could be a cost to, again, being more environmentally friendly or greener, right? There's a cost to installing solar panels. There's a cost to using wind energy and setting up those turbines, right? There's a cost to, again, doing things like recycling, right? Every minute you spend sorting your trash is a minute that you're not spending making your products faster, better, and cheaper. And sometimes those costs might be worth it, and sometimes they might not, according to, again, what the business's goals are, right? But either way, there's still some abatement costs when it comes to cleaning up that production process. And that picture on the right is actually a invention that was developed. It's a machine that is powered by a water wheel that helps clean trash out of a river in Baltimore. As you might imagine, it costs money to build and staff such machines. And so again, this could be part of those types of abatement costs when it comes to removing parts per million out of the water, or again, reducing maybe those ambient concentrations. So whether it is a business that's trying to reduce its amount of emissions through producing things in a more environmentally friendly way, or whether it's inventing technology or using it to reduce the amount of ambient concentration of pollutants in our atmosphere, either way, there are costs to getting rid of these emissions, right? So keep that in mind. These abatement costs are certainly going to play a role in determining what the optimal amount of pollution should be. Right, now our marginal abatement cost curve shows the added cost of achieving a 1 unit decrease in emission level, or again, if you're talking about those ambient concentrations, it's a 1 unit decrease in the ambient concentration in the environment. So our marginal abatement cost can be calculated as the change in abatement cost divided by, again, the change in emissions, being the emissions that we are reducing. Now, before we get into this graph, I want you to kind of brace yourself. Right, our marginal abatement costs, because we're talking about the number of emissions that are being reduced, when we have we're measuring emissions on our x-axis, they're going to slope upward from right to left, which is not something we're used to seeing. We're used to kind of reading graphs from left to right. So this might blow your mind a little bit, but again, I'm going to kind of walk you through why it's going to look the way that it is going to look. So with that in mind, let's go ahead and graph them out. So I'm going to go ahead and draw two graphs here. So in your notes, if you're following along at home, I want you to also draw two graphs side by side. I'm going to use red there. Let's start them out here in black. So in your notes, you're going to have two graphs side by side, and these graphs are going to be kind of mirror images of one another. Right, both graphs we're going to be measuring damages in terms of dollars on the vertical axis. Right, now in the first graph we're going to be looking at the quantity of emissions reduced. Whereas on this graph on the right, we're just going to look at the total number of emissions. E, which is kind of what we've been looking at in our other graphs. Okay, so obviously if we're not reducing any emissions, then we're not going to have any marginal abatement costs. Remember, marginal abatement costs are the costs of reducing emissions. If we haven't reduced any, then you're not going to have any costs of reducing those emissions. And then the more emissions you do reduce, the more your abatement costs are going to be. So you could have a marginal abatement cost curve that's going to look something like this, right? Basically saying that, hey, as we reduce more emissions, our costs are going to be higher. In other words, that might be the marginal abatement cost of reducing 10 emissions, right? This might be the marginal abatement cost of reducing 15 emissions, and this might be the marginal abatement cost reducing 20 emissions. The more emissions we reduce, right, then the more those abatement costs are. Right. Now, with that in mind, how is this going to transfer over to a graph where we're measuring the total number of emissions? Right. Well, let's say that 20 is the maximum here, number of emissions out there. Well, if we reduce 20 emissions, then that's the same thing as having 0 emissions, right? So if there were 20 emissions possible and we spend all this money to reduce all 20, then we have 0 emissions, right? So this curve is going to look like this in such a way where it's going to be the opposite or mirror image of the other curve, right? So with that in mind, here where we reduced a total of 15 emissions out of the 20 possible, if we take away 15 emissions out of the 20 possible, that means that we are left with 5. And if we take away 10 emissions out of the 20 possible, then we're going to be left with 10. And of course, if we don't take away any emissions out of the 20 possible, then we're left with the maximum number of emissions, which is 20, right? So again, this graph on the left is just a mirror of the graph on the right. If you were to kind of fold that graph over from the left to the right, then you'd see, again, that they pretty much overlap. So with that in mind, again, the way we read our marginal abatement cost curve is we read it starting here when we have 20 emissions. That means we're not abating any. And then it increases as we move from right to left to the point where if we're abating all of our emissions, then you're going to have 0 emissions left, right? So again, if we're measuring the number of emissions and not the number of emissions reduced on the x-axis, then this curve is going to increase from right to left, which is a little bit different than how we're used to reading graphs in an economics class. Right, so again, try not to let that shock you or blow your mind too much, but it is kind of the way we're going to be looking at it moving forward. All right, so that's what your marginal abatement cost curve looks like. Now, let's use our marginal abatement cost curve to find total abatement costs. In the same way that your total damage cost is the area under your marginal damage cost curve, right, your total abatement cost can be measured as the area under your marginal abatement cost curve at any particular level of emission. So once again, the total is just the area under that marginal curve. That's true whether you're talking about damage costs or abatement costs, right? As similar to our marginal damage cost curve, if our marginal abatement cost curve shifts up, then that means it is more costly to reduce the next emission and that our total abatement costs will be higher, right? And what usually shifts our marginal abatement cost curve is changes in technology. So assuming that we are dealing with the same pollutant, so we're talking about the same type of pollutant out there, the location of our marginal abatement cost curve, whether it's shifting up or down, is usually influenced by technology. Generally speaking, technology makes it cheaper and easier to abate these emissions or get rid of this pollution. Let's go ahead and graph out what this marginal abatement cost curve looks like and how that tells us what our total damage costs are. So we'll go ahead and draw a graph similar to the one that we drew earlier. So again, we are looking at damages as measured by dollars on the vertical axis and then emissions on the horizontal axis, right? So again, there is a maximum number of emissions, which we're going to call E bar here. This is the most emissions possible. And then as we reduce emissions, then our marginal abatement costs are going to increase. Again, in this direction as we go from right to left. So we'll call this marginal abatement cost 1. Right, so what happens if we are at, say, E1 here? Well, again, at E1, if we go up to our marginal abatement cost curve, then that is going to tell us the cost of getting rid of another emission when we're already at E1. Right, we'll say for the sake of argument that maybe that's $50. And again, if you look at the area under our marginal abatement cost curve, between the maximum number of emissions possible and the number of emissions we have, that area represents the total abatement cost. We'll call this area A here, right, of getting rid of that number of emissions. Right, so again, if we're looking at MAC1, at E1, right, if we reduce emissions to E1, again, we're reducing emissions to E1 is the way to interpret this. Then our total abatement costs is going to be equal to area A. Right. Also, reducing emissions by one more unit when we are already at E1 is going to be equal to that $50. Again, that's the marginal cost of reducing another emission when we've already reduced emissions down to E1. Now again, what would happen if our marginal abatement cost curve were to increase for whatever reason or shift up? Let's say that we had a marginal abatement cost curve that looks something like this. So again, when we're at E1, or we've reduced emissions from E bar, which is the maximum number of emissions, down to E1, then the cost of reducing another level of emission is going to be higher given that that marginal abatement cost curve has shifted up. And again, there's going to be some extra damages, some extra abatement costs. So our total abatement cost is going to be higher here as well, if we call this area B. Right, so in other words, how do we interpret what's happening when we're at E1 here? So let's change my notation real quick. So this is E1, not E primed. I don't want to confuse anybody there. My one was just a little high up on the E. All right, let's go back here. So what happens if we're at E1 but following that MAC2 curve? Okay. Well, again, reducing emissions to E1 is going to have a cost to it. Our total abatement cost of doing this is going to be equal to areas A plus B now, right? Again, it's the entire area under that marginal abatement cost curve that we're focused on at the number of emissions, right? And then reducing emissions by one more unit. When we're already at E1 is going to be equal to $100. Right, so again, that marginal abatement cost curve not only tells you what the total abatement costs are as the area under that curve at the number of emissions, but it also tells you what is the cost of reducing another emission, right, at the number of emissions in question. So keep that in mind because that's going to become important too as we figure out the optimal level of pollution. Right, so that's what the marginal abatement cost curve looks like and how to interpret it. And make sure you know that moving forward. All right. So let's talk about what the socially efficient level of emissions are, or the optimal level of pollution. Right. So again, we've talked about the damage costs, and now we've talked about the abatement costs. Right. True to economic form, you're going to want to find an equilibrium. So to minimize the total cost of pollution, you want to set the marginal damage costs equal to the marginal abatement costs. Right, and then that's where you're going to find out what level of pollution is best for society, taking into account, one, the damage caused by that level of pollution, and two, the cost of getting rid of pollution. Right. Now, as you're doing this, you should be able to find total pollution costs, and that's just going to be your total damage costs plus your total abatement costs. Right, so again, the area under that marginal damage cost curve at the optimal number of emissions, as well as the area under that marginal abatement cost curve at the optimal number of emissions. If you add them together, you're going to get the total pollution costs, which includes not only the cost the pollution has towards the environment, but the cost of getting rid of pollution down to that level as well. Right, so again, there is damage costs in terms of what it's doing to the environment, as well as abatement costs in terms of the cost of cleaning up the environment, right? Going from a less healthy environment to a more healthy form of production process, right? There are costs associated with those abatements, right? And you've got to kind of find an equilibrium between those two. So let's go ahead and talk about how to do that, right? Let's find ourselves the optimal level of pollution using a graph. All right, make sure you leave yourself plenty of room to go through this graph. As we're going to be doing a lot with it here, right? So again, you're going to be measuring dollars up here, and you're going to be measuring emissions down here. You're going to just use that letter E to do so, right? So again, you might have a marginal damage cost curve that looks like this. Right, and we'll call this E hat. Again, E hat kind of represents the assimilative capacity of the environment, or what we usually call the threshold level of emissions. So again, E hat is our threshold. level of emissions, or the amount of emissions that the Earth can handle given its assimilative capacity before it suffers any undue negative effects, right? And then we're going to have a marginal abatement cost curve that looks something like this. Again, it's going to increase from right to left. And where that originates, we're going to call that E primed. And we're going to say that E primed represents an uncontrolled level of emissions. Or in other words, the most emissions possible if we didn't try to control them at all. So you can think of this as like the maximum amount of emissions. Right, so that's kind of the maximum amount of emissions if we didn't try to control our emissions at all. And then where these two curves intersect, we're going to get E star, and E star is, you guessed it, that optimal level of emissions. And where those two curves intersect, right, that's where our marginal abatement costs are going to be equal to our marginal damage costs. Right, so right now I'm just kind of giving you the theory of the graph. We're not going to go through the math just yet. I want to make sure you understand what this graph looks like before we do go through that math, right? But just to give you an idea, right, you're going to be setting your marginal abatement cost curve equal to your marginal abatement cost function equal to your marginal damage cost function in order to calculate what that optimal level of emissions are, right? So in other words, in order to minimize costs, you're going to have to set MDC equal to MAC. This is going to minimize our pollution costs. All right, so hopefully that's making some sense here. So let's go ahead and calculate out what these pollution costs are going to look like, right? So total pollution costs are going to be equal to our total damage costs plus, I'll try to squeeze this in here, our total abatement costs. All right, now how do we find out where those are? Well, our total damage costs are going to be the area under our marginal damage cost curve, again, at the optimal number of emissions. So if we're looking at this, it's going to be this area here. Right, that is the area under our marginal damage cost curve, which is right here at the optimal level of emissions. So we're going to go ahead and call this area A. Right. So again, our total damage cost here is going to be area A. Now we got to add to that our total abatement costs, and that's going to be the area under our marginal abatement cost curve at the optimal number of emissions. So we've gone from E prime down to E star. That's how many emissions that we have abated, right? So again, the area under our marginal damage, or sorry, under our marginal abatement cost curve here, all this area B, right? That is going to be your total abatement costs. Right, so if you're wondering what your total pollution costs are, that is going to be area A plus B. Right, or the area of this entire triangle here, right? So again, if we were to call this P here, call this here point just P, just to label it something, right? Then if you're wondering kind of how to break up these triangles, right, our total damage cost is the triangle bounded by area E hat, E star, and P, right? Our total abatement cost is the area bounded by E star, E primed, and P. And then our total area here that we're looking at for this triangle is the triangle bounded by E hat, E primed, and P. Right, so again, that's the triangle that we'd be looking for if we're measuring that one there. And just to be clear, we're talking about triangles here as well when we're talking about these areas that we're measuring. All right, so again, that is what the optimal number of emissions is going to look like, and again, how to figure out the total pollution cost as the total damage cost plus the total abatement cost when we are at that optimal number of emissions. Now, why is that the optimal level of emissions or the optimal amount of pollution? What would happen if we were to operate at some point that wasn't E star? How would that affect these areas and this graph? So at the risk of potentially confusing you, let's go through some hypothetical examples of what it looks like if we are not at the optimal level of emissions. Like what if we are at a number of emissions that is too high? So let's say that we're operating here at EH. And EH is just, again, a number of emissions that is higher than our optimal amount of emissions, right? So what happens at EH? Which again are just emissions are too high. Right. Well, when we're at EH, again, you have to go up to the marginal abatement cost curve to get the abatement cost, and up to the marginal damage cost curve to get the damage cost. Again, recognize that those are no longer equal to one another. Right. So again, if we're trying to figure out what are the abatement costs here, when we're at EH, then you have to look at the area under the marginal abatement cost curve, which in this case is going to be this area here. So we're only reducing emissions from E primed down to EH. So we're just going to call that area F. Our total abatement cost in this particular case is just area F. Right. So notice that our abatement costs appear to be a lot smaller, but what's our damage cost going to look like here? So let's take a look at our total damage cost in this situation. Well, now remember that our total damage cost is the area under the marginal damage cost curve at the number of emissions that we are choosing to have, right? Which means it's got to include this entire area here as well. So we'll call this area C, because this is now under that marginal damage cost curve when we're at EH. So our marginal damage, our total damage costs are going to include the areas A, plus B, plus C. So our abatement costs are lower when we allow a higher number of emissions. That should make sense. We're abating fewer emissions, so our abatement costs are going to be lower. But our damage costs are going to be a whole lot higher, right? We're going from just area A to area A plus B plus C. And notice that the total area, when you add both of them together, is going to be much more extreme than it was when we were at the optimal number of emissions. Right, so we're saving area B in abatement costs, right? But we're increasing our total damage costs by areas B plus C, right? So again, we're saving area B from abatement, but we're increasing damage costs by area B plus C, which means all we're really doing is shifting some of those abatement costs over to damage costs, as well as adding an entire area C to our costs that didn't exist before, right? So again, we're going to be much better off from society's perspective at E star than if we were at EH. Now, what happens if we are at a lower level of emissions? Right, we'll call that EL. So E, we'll do a subscript this time, L. Right, what happens if we're at EL where emissions are too low? Well, again, wherever we're at in terms of the number of emissions, you go up to our damage cost curve in order to figure out the damages caused by that number of emissions. And then you have to go up to your marginal abatement cost curve to figure out what are the abatement costs at that number of emissions, right? And so let's go ahead and take a look at these different areas. And before we do that, let's go ahead and label this extra area here that we're going to need to talk about, call that area D, right? So with that in mind, let's take a look at our total abatement costs. So remember, our abatement costs are the area under the marginal abatement cost curve at the number of emissions that we're talking about. So if we're at E subscript L, right, then the area under our marginal abatement cost curve would include areas A, plus B, plus D, plus F, right? So again, we're talking about the area of this triangle here. Right, that would be the area under our marginal abatement cost curve when we are at EL. Right, now in order to figure out our damage cost, well, that's just going to be the area between E hat and EL there, or the area under our marginal damage cost curve. We'll go ahead and call that area G. Right. So notice that when we have a lower than optimal number of emissions, our damage costs are lower than they otherwise would be, but now our abatement costs are really high, and our total costs are again going to be higher than they otherwise would be. So we save area A in damage costs. But unfortunately, we're going to be increasing our abatement costs by area A plus D. Right. So again, compared to the optimal number of emissions, right, we've reduced our damage costs, but we've shifted those damage costs over to our abatement costs. And then we've added this area D that didn't exist before when we were at the optimal level of emissions, making our costs more expensive, right? So keep that in mind. By the way, if you are looking at a still picture of this graph, then our total damage costs when we're at EH will now also include area G. So again, we could like, if you're looking at the total picture at the end of things, then you'd have to throw that area in there that we didn't segment out before. But in any case, the idea here, hopefully as you're looking at this, is that we minimize these total pollution costs in terms of our damage costs and abatement costs added together by operating at the optimal number of emissions, E star, which is where our marginal abatement cost curve intersects our marginal damage cost curve. Right now, of course, there's a lot of math that we can do to help us figure out what that is, and that is what we're going to do in our next lecture video coming up. Right, but for now, I want to make sure that you all understand this much, right, in terms of how to look at this graph and how to figure out what those optimal number of emissions are just by looking at a graph before we get the math involved. But when we come back for our next lecture video, we're going to go through an example of calculating the optimal number of emissions. In fact, we'll go through a couple just to make sure you know how to do it. And then we'll talk about how enforcement costs and technology will affect that optimal number of emissions. We're also going to talk a little bit about combining the idea of the equal marginal principle with minimizing abatement costs and achieving those optimal number of emissions. So all that will be in the second part of the lecture videos for this chapter. But for now, I think that should be good enough. Just let me know if you have any questions. Feel free to shoot me an email or come visit me in those Zoom office hours, and I'll be happy to answer any questions that you might have. But till then, let me know if you need anything. Take care.